session this morning. And so when we conclude our training today, what we're going to be doing, we're going to go ahead and house this recording out on our YouTube channel where we do our videos out there, and it'll be called Session 4 Heat Pump Defrost Demand Control Review, and then today's date, 02/25/2021. So this time I'm going to go ahead and share my screen, and we're going to, we'll get our PowerPoint coming up this morning on our defrost control. Okay, so this morning, again, we want to welcome you to the program today. We're going to be doing Session 4 Heat Pump Defrost Control Review this morning. And so let's go ahead and get this started. So Jill, can you see that okay? Can you see the, I'll let you kind of be my monitor like as normal.
Yep, everything looks good.
Everything looking good, okay. All righty. Okay, so today, team, we're going to be talking about specifically the demand defrost control. This is the most common controller that we have on our product. As a matter of fact, if you look at our 14 SEER heat pump, for instance, our single stage heat pumps, you're going to find that, which is what we sell the most of it when supply, you're going to find that this is going to be the type of defrost control that you're going to have on there. In addition, this defrost control, it may have a little different look than what we're actually going to be looking at today as far as the actual picture. I noticed in our technical conference yesterday that we were doing a review on a defrost control. It had all the same functionality as this control, only it was a green board instead of a brown board. But as far as functions, they're all going to be the same. So if you happen to get a brand new piece of equipment and the board is green instead of brown, that's okay. It's still going to have the same inputs and outputs. It's going to have the same type of wiring and the jumpers and stuff like that. So today we're going to talk a little bit about demand defrost controls again, but we're also going to cover defrost control principles. We're just going to overview quickly the difference between a demand defrost control and a time temperature control. In addition, we're going to talk about the electrical inputs and outputs of the demand defrost control, as well as thermistors and nominal calibration points, and then of course forced defrost modes as well for servicing. So some of the things I'd like everybody to kind of write down or at least put in your memory, that as far as our demand defrost control is concerned, you're going to have a minimum of 40 minutes since the last defrost. And this is the reason we do this is if you have a bad sensor, you don't want to just be cycling back and forth between defrost cycles and not getting any work done. So there's a minimum of 40 minutes since the last defrost. In addition, the outdoor sensor is going to have to be below 40 degrees Fahrenheit. So this is a really important concept, from a service standpoint, especially. Before this defrost control even thinks about defrost, it has to be 40 minutes since the last defrost, and the outdoor air temperature has to be below 40 degrees. So if it's 50 degrees outside, it doesn't even think about defrost until it hits below 40. In addition, defrost termination is going to take place when the coil sensor reaches 55 degrees. And by the way, there is another position on what we call the P5 jumper. On position 4, it'll actually take it up to 80 degree termination. But normal defrost termination is going to occur when the coil temperature sensor reaches 55 degrees Fahrenheit. Plus, in case you have a bad coil sensor, there's going to be a maximum defrost time or a time backup of 14 minutes if that is reached prior to the liquid line reaching that 55 degree termination point. Any questions or comments on that so far? Okay, good. All right, so as we take a look at the demand defrost control, I'm just going to kind of keep the picture up here a little bit as we talk about some of the differences between a demand defrost control and a time temperature control. The big difference between a demand defrost control, you'll notice in the upper right-hand corner of the picture, you're going to see that there's two sensors. It says coil and ambient. And so a demand defrost control is always going to have a coil temperature sensor It's also going to have an ambient or an outdoor air temperature sensor. Now, what happens is this on the demand defrost control, it's going to be constantly comparing the outdoor air temperature with the ambient sensor and the coil temperature sensor with the coil sensor. It's going to constantly be monitoring those sensors. It doesn't matter even if it's 100 degrees outside and we're in the cooling mode of operation. It doesn't matter. Those sensors are alive year round, no matter what the temperature is. Now, once the outdoor air temperature reaches 40 degrees or colder, it'll start thinking about defrost. But once it starts looking at the defrost, or more specifically, when it starts looking at outdoor temperature, it's also comparing that outdoor temperature to coil temperature. Then once the coil temperature and the outdoor temperature reach a certain pre-engineered parameter, the difference between outdoor air temperature and coil temperature, once that difference is reached, there's going to be a difference there. Once a pre-programmed and pre-engineered difference between those two temperatures are met, it'll then go into defrost. Now, these are some basic principles with every defrost control. Whenever the unit goes into defrost, a couple things are going to happen. Number one, it's going to switch the reversing valve to the cooling mode of operation. So we're going to put the unit in cooling mode. The outdoor fan's going to shut off. And then we're going to have an output from what we call W out on the board, which we'll talk a little bit more later. We're going to output 24 volts from the board to bring the heat strip on inside, or bring the auxiliary heat on if it happens to be a dual fuel system with a furnace. It'll output W from the board, or W out from the board, to bring on the auxiliary heat during defrost, so you don't freeze the homeowner out during defrost. Because remember, when you go to defrost, you're actually going into the air conditioning mode to defrost that outdoor coil. So one more time, whenever we go into defrost, we're going to shut the outdoor fan off. The reversing valve is going to switch into the cooling mode of operation, and we're going to output a signal from the board outside to bring on auxiliary heat to temper the air so you don't freeze the homeowner out during defrost. So again, the demand defrost control has two sensors, a coil sensor and an ambient sensor, and those sensors are constantly being compared. Those temperatures are constantly being compared as far as when to go into defrost. Any questions or comments on that basic concept before we talk about the old time temperature control for just a minute or two? Okay, well, let's talk a little bit about the old time temperature control. So a time temperature control is different than a demand defrost control in the fact that it does the same functions as far as shutting the outdoor fan off and going into the air conditioning mode during defrost. That all stays the same. However, how it gets to defrost is different. So a time temperature control, what it does is it has a simple clicks-on switch, or a temperature switch, mounted on the lower coil pass of the outdoor coil. And the defrost control is just sitting there monitoring that switch. Once the outdoor temperature reaches about once the coil temperature reaches about 30 degrees, that switch is going to close on a drop of temperature, and then it's going to start timing the amount of run time after that switch closes. So here you've got this heat pump outside. It's in the heating mode of operation. The outdoor coil's cold. It's starting to build up some ice. Once that outdoor coil reaches about 30 degrees temperature, that little switch closes on a drop of temperature. Once that switch closes, it's a physical switch, it's 24 volts, click. Once that switch closes, it'll start a timing sequence, and it starts monitoring the run time on the outdoor unit. Then once a specific run time is met, and there's a field selectable jumper, by the way, typically 30, 60, and 90 minutes. Once that time is met, wherever that jumper is set, 30, 60, or 90 minutes, once that time runs out, it'll then go ahead and go into a defrost. Once it goes into a defrost, it'll do the reversing valve. It'll go into cooling mode of operation, shuts the outdoor fan off, brings the auxiliary heat on so you don't freeze the homeowner out, and the thing is in defrost. It'll then stay in defrost until that switch on the outdoor coil comes up to about 55 to 60 degrees Fahrenheit, and then it'll open electrically, it'll open electrically, and once it does, it terminates the defrost and resets the timer. So the big difference between a time temperature and a demand defrost control is the time temperature control just has a simple little clicks-on switch, click, 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 mounted on the coil outside to monitor the temperature of the coil. It does not have an ambient sensor. The other difference is that the demand defrost control, because it's constantly monitoring the difference between outdoor temperature and coil temperature, it has more of a tendency to defrost the coil as needed, not so much just strictly driven by a time function. Any questions or comments on those two defrost control principles before we continue with our layout and actually start digging into the demand defrost controls, all of the inputs and all of the outputs before we move on? Any questions or comments? Well, okay, team, let's go ahead and jump into this defrost control then, this demand defrost control. As I said, this is a very common type of control. As a matter of fact, most manufacturers anymore use a demand defrost control because it is more efficient, because you're not defrosting quite as much throughout the day. It has a tendency more to defrost on an as needed basis because it's looking at outdoor temperature and coil temperature. And so it has more of a tendency to defrost as needed, not so much just strictly on a time. And so that makes it a little bit more efficient, because if you think about it, anytime you go into the air conditioning mode in the middle of the winter time and you bring on auxiliary heat, so you're air conditioning and you have auxiliary heat on, that's not a really efficient mode to be in. And so you're basically heating and cooling at the same time, and so that's not real efficient. So we try to reduce our defrost as much as possible on a heat pump. We want to make sure we defrost it enough to where it's going to stay efficient and the coil's going to stay clear and all that. But at the same time, we want to make sure that we're going to let some ice build up on that coil before we go into defrost, and then we're going to defrost it when we need to. And that's really the main thing about a demand defrost control. It's really designed to defrost on an as needed basis, not so much just because you think the coil's got a little bit of ice on it. So as we take a look at our demand defrost control a little bit closer, we see that we're going to have a low voltage harness. Now, this low voltage harness is where we're going to receive low voltage signals on terminals R through W. Now, it should be noted, W out is an output for the heat strip operation or the auxiliary heat during defrost operation. So what we're going to do, we're going to kind of blow that up a little bit, and let's look at each input and each output. And remember, team, this is going to be a harness plugged on with about a 6 or 8 inch pigtail to make your low voltage wires up from your thermostat and your indoor unit. So you'll see that we blew that up a little bit to give us a little better look at those pins or those terminals. Now remember, team, I've removed all the harnesses off this board so that we can talk about. So where these pins are, you'll actually have a harness that'll be wired in such a fashion you'll actually have wires coming off this harness. But we went ahead and took that harness off so that we could talk about each one of those pins, inputs and outputs individually. C is our 24-volt common that's going to be powering the board up. That'll be one side of the board being powered up all the time. Now remember, team, the demand defrost control has to have power to it all the time for it to function. So even in the dead of summertime, it's in the cooling mode. It doesn't matter. It's still monitoring those sensors, and it still needs power to that board on C and R year round. So again, C is 24-volt common. Right next to him is going to be our R, which is our 24-volt hot that powers the board up. And one more time, remember, this board has to be powered up year round. O terminal is an input from the thermostat for reversing valve operation. Now, it should be noted on our Champion equipment, anytime we energize the O terminal, we're going to be in the cooling mode of operation. So O is our input from the thermostat for reversing valve operation to switch to cooling mode. Y terminal is the input from the thermostat for compressor operation. Now, it should be noted, it doesn't matter if it's heating or cooling mode, that compressor is going to be running. The only difference is that in the heating mode of operation, the O terminal will not be energized, but we'll still have the Y input because we're still going to have that compressor running on the heat pump in the heating mode of operation. So Y is our input from the thermostat for compressor operation for both heating and cooling mode. W is an input from the thermostat for supplemental heat, and it's the demand from the space. So basically, once the thermostat sees a call for supplemental or auxiliary heat, it'll send a signal out to W terminal, and then that W terminal is just a relay on board that defrost control board that's going to loop that W signal through the defrost control board back out to what we call W out. Now the W out is an output. By the way, this is the only output from the board. This W out is an output from the board for supplemental heat demand from the space, and it's also going to be energized during defrost mode. So it serves two functions. In one function, when you get a W from the thermostat that we just talked about, when you get a W on the board, it's going to loop it out through a relay and send it right back inside to bring on the auxiliary heat. Also, when the unit goes into defrost, this is important, when it goes into defrost, it's going to output a W out from the board to bring the auxiliary heat on during defrost. Now, you remember I mentioned there was a relay on board out there. So the W and the W out loop through is through a normally closed relay. But now watch this. When it goes into defrost, that relay switches, click, and then it takes Y signal. In other words, the compressor has to be running during defrost. So during defrost, it takes the Y signal and loops it out through W out. And so that's the main difference that we got to remember, that during defrost, our power source during defrost for the W out is actually the Y terminal. But during normal operation, just during normal operation, if you go to auxiliary heat, it's going to loop the W through the W out during normal operation. But during defrost, we actually steal the Y signal to ensure that the compressor is running. We take that Y signal and loop it out for auxiliary heat. So it's just a little interlock relay that ensures that the compressor is running during defrost. So when we're in defrost, we know the compressor has to be running, otherwise we won't get auxiliary heat. And then during non-defrost operation, if we get auxiliary heat, we have to pick that up from a thermostat call going to, actually calling for auxiliary heat. So that's the difference between the W and the W out and the Y and the W out circuitry internally. I know it sounds like there's a lot of stuff there to think about, but is there any questions or comments on what we've talked about so far?
No, we're good.
Everybody good? Okay. Just wanted to clarify that a little bit on the W and the W out and the Y and how all that worked, because, a lot of people, a lot of contractors say, well, gee whiz, why do I need that Y or that W outside? And the truth is, you could get by without the W going outside and just let the thermostat control the auxiliary heat, which is fine. But always remember, no matter what, whether you use that W circuit or not from the thermostat outside, you always, please write this down, you always want to bring W out from the outdoor unit inside and hook it up to your auxiliary heat, because that's what's going to bring the auxiliary heat on during defrost. Because if you forget to bring that W out in and hook it up to your auxiliary heat, what's going to happen, you're going to freeze the homeowner out every time it goes into defrost. So always bring that W out in for your auxiliary heat during defrost. Okay, good. So let's go ahead and start kind of taking a tour of the board and the sensors and the pressure switches and so on. You'll notice on the top of the board, as we take a look at our photo, we have an HPS and an LPS. That's our pressure switch terminals. Those are inputs and outputs to the pressure switches. You'll notice, if you look closely at the photo, you'll see that the pin spacing is different between the high pressure switch and the low pressure switch. And the reason they do that is so you can't mess them up. If you take if you try to plug the high pressure switch onto the low pressure switch, it's not going to work, and so on. So that pin spacing is different. And so that's our input output from the board for our pressure switch terminals. Now, it should be noted, all of our heat pumps are going to be coming with a low pressure switch and a high pressure switch for safety. Right next to that, you're going to see there's RV terminals. Those RV terminals are for the reversing valve. And again, it doesn't matter. You'll notice the pin spacing is the same there. So the plug will go either way, but that's right. It's just a 24-volt output to the reversing valve that we're going to output from the board in the cooling mode of operation for the reversing valve. Right next to that, you're going to have a couple of terminals called CM. Those CM terminals are outputs from the board down to the compressor contactor. And so we're going to bring the compressor contactor on with an output from the board on the CM terminals. Now, it should be noted, there's going to be a built-in 5-minute anti-short cycle delay. So the defrost control has a built-in anti-short cycle delay of 5 minutes to prevent the compressor from being cycled on and off too often. And so CM will output after that anti-short cycle delay is timed out. So let's say, for instance, you've got a compressor operation, you have a Y signal, the unit's running, the unit shuts off, and a kid's maybe playing with the thermostat. And so we don't want that. We don't want the outdoor unit short cycling just by, somebody playing or messing around with the thermostat. So there's a built-in anti-short cycle timer to give the compressor a chance to just settle down and the pressures to equalize and the oil to stabilize and all that kind of stuff before we bring the compressor right back on. So there's a 5-minute anti-short cycle. Now, please make a note of this. From a service standpoint, if you jumper the test pins, which we'll get to in a little bit to force a defrost, if you jumper the test pins, that bypasses the anti-short cycle timer for testing purposes. Right next to that, we're going to have a couple. There's our ambient and coil sensor inputs. Please notice, team, that the spacing on those sensors are different. And again, it's the same routine. We want to make sure that the ambient sensor doesn't get plugged onto the coil, and we don't want the coil sensor plugged onto the ambient. So if you look closely, you'll notice that the pin spacing is different on the coil and ambient sensors. Now, it should be noted those sensors have the same calibration point, which we'll talk about later. But the demand defrost control has to have both sensors working properly in order for it to defrost properly. So coil and ambient sensor are going to be plugged in on the board right there. And another little side note, if you remove the sensor from the board, you can always take your voltmeter and you can check the voltage on those pins. And the voltage on the pins should be about 4 to 5 volt DC without anything plugged on. So if I remove a sensor, that's actually a pretty important check. You remove the sensor and check the voltage on those pins. It should be 4 to 5 volt DC. Now watch how easy it is to troubleshoot this board. If I have 24 volts on the board between R and C that we talked about earlier, common and hot, 24 volt hot. If I've got 24 volts on the board and I unplug the sensors from that board, and I should read 4 to 5 volt DC on those pins. If I don't, you don't have to go any further. It's a bad board. The DC power supply has failed, and it's, the board's bad. However, if I do have 24 volts on the board, and this is year round, by the way, team, as I said, we power the board up year round. If I've got 24 volts on the board and I remove the sensors, the coil and ambient sensor from the board, and I read the pin voltages for the coil sensor and the ambient sensor, and I have 4 to 5 volt DC, and I can go down to the test jumper and I can put the thing into a defrost. If I can force a defrost and I've got 4 to 5 volt DC on the sensors, it ain't a board. The board's probably okay. You have a 95% chance or better the board's fine if you can force a defrost and the sensor output voltage of 4 to 5 volt DC, the board's okay. It's something else. It might be a sensor or whatever that's gone bad. But just kind of keep that in perspective. One of the things I really, really like about our Champion and Johnson Controls products here is it's so easy to troubleshoot. If I got 24 volts on the board and I got 4 to 5 volt DC on the sensor outputs and I can force a defrost, the board's okay. Anyway, any questions or comments so far? Everybody good? Okay.
Oh, we're good.
All right, team, as we move around the board, we're going to see that we've got a defrost curve jumper. This defrost curve jumper is going to be set on one of those pin numbers based on the tonnage of the unit. Now, it wouldn't be so easy as just 1 ton, 2 ton, 3 ton, 4. That isn't how that works. So basically a 3-ton unit might be on position number 1, a 2-ton unit might be on position number 3. You get the idea. But basically, defrost curve pins are going to be used for best performance of the heat pump depending on your location. Now, pins 1 through 3 have a defrost termination of 55 degrees. Now, by the way, they're going to be set somewhere from the factory, and we recommend that factory setting. However, we do give you an auxiliary pin number 4, and what that is, that pin number 4 jumper is a termination of 80 degrees. And so you'd have to have a pretty special application to where you'd want to have an 80-degree termination point. I don't know, maybe if you were in Arizona or something like that, you know, the high mountains of Arizona where it's super, super dry and you don't build a lot of ice up, and you want a little bit more of a termination point. Or maybe you have freezing rain freezing rain in Tennessee, and you want to have a higher defrost termination point. The point is that I recommend leave it where it is, unless you have a real good reason to change that to 80-degree termination. Because if you put it on the 80-degree, pin number 4, 80-degree termination, what's going to happen most of the time is you're going to be going out on not time temperature, excuse me. You're going to be going out on a time backup of 14 minutes. And so if you move it over to 80 degrees, what's going to happen, it's going to sit here and cook and cook and cook and defrost and all that stuff until you hit the time backup. And that's the most inefficient way to defrost, because most of the time, if your defrost control is working properly and the sensors are okay and all that stuff, typical defrost is going to be somewhere between about 4 to 7 minutes, but you have a 14-minute backup. So just be aware of that. If you move that, if you think you're going to move it to pin number 4, and I'm going to get an 80-degree termination, and that's going to give me, an absolute defrost every time. It's going to use up more energy, because remember, in defrost mode, team, you're in the heating and cooling mode at the same time, so you're going to be burning up a lot of energy, and you're going to be hitting that 14-minute backup before you reach 80 degrees, I'm going to guess, on your termination points. But that jumper is there for special application. Now, it should be noted, too, I noticed the other day when I was looking at our tabular data information. So if you go to Navigator and you go to your equipment catalog and so on, and you pull up the tabular data sheet, which is normally going to be page number 2 and 3 in your technical guide on the equipment, you're going to notice that on the heat pumps, on the tabular data, they're going to tell you the defrost curve pin jumper position. That's something new on the tabular data that I hadn't noticed before. And so if you're ever going to wonder, well, gee, where should that jumper be? I put a brand new board on and I forgot to look at it from the old board. You can go to your tabular data for the outdoor coil or for the outdoor unit, and it will tell you on the heat pumps where the defrost curve jumper should be. So we always recommend put it on the factory setting unless you have a really good reason to change that. Any questions or comments on the defrost curve and how we can change that in the field with a jumper selection?
Any significant difference between the pin settings of 1 and 3, or are those all just the same, set at that 55, no difference in time, temperature, or anything like that?
That is a really, really good question. All right, so what it is what they call a defrost curve. And so even though the temperature termination point is going to be 55 degrees on pin number 1 through 3, how that thing defrosts, and specifically what it looks at as far as outdoor temperature, ambient temperature, there's a pre-programmed algorithm in there that's a little bit different between the tonnages. And what they do is when they're in the halt facility or in the test facility, when we're testing the equipment, there's going to be an optimal curve. There's going to be an optimal place. To give an example, let's say a 3-ton unit. I'm just making this up, but to give it as an example, let's say a 3-ton unit, the optimal outdoor air temperature, let's say at 20 degrees outside, and the optimal coil temperature might be 15 degrees before it goes into defrost on that coil and that chassis, that combination. But on a 2-ton, let's say if it's 20 degrees outside again, the optimal coil temperature for defrosting and getting the coil clean and making sure the coil's clear and all that kind of stuff might be a 17 degrees. So it's always going to be it's not a linear line, it's a curve. And so based on the tonnage and based on the SEER rating and based on the compressor efficiency and based on all that engineering mojo, there's going to be an optimal place in that coil and that ambient temperature curve to defrost that unit. So the reason we give you different pin selections is because based on the tonnage of the unit, you're going to get best performance and optimal defrost over efficiency by having it on the proper pin setting. That's why they do that. But that was an excellent question. Did I answer that question okay?
Yeah, no, that was perfect. Thank you.
Okay, got it.
So pretty much in central Illinois, we're gonna leave those pins alone.
Yeah, thank you for that good observation. So our recommendation is even though you have a termination point of 55 degrees, the optimal curve for each tonnage will be at that factory setting from the factory. So we're going to recommend, if you have to replace a defrost control board, make sure and observe, where the pin settings are, for that on the defrost control board for optimal operation. Good. Excellent point. Any other good questions or comments?
Oh, we're good.
Good, excellent. Okay, team, as we move around the board, here we have our condenser fan terminals. Now, it should be noted, please be aware this is the only high voltage spot on the board. So it's, we're going to give you a good warning right here. This is high voltage because these are the condenser fan terminals. More specifically, you can see it's a big relay on the board. This is what shuts the outdoor fan off during defrost. And so this condenser fan terminals are going to be high voltage, team. So please be careful if you're working on this board, and be aware that those are high voltage terminals, because all we're doing is we're just breaking one side of the condenser fan motor. And of course, that condenser fan motor, based on the product, could be up to 230 volt. And we're just breaking one side. So you could have, basically 110 volt to ground on these terminals. So please be careful from a service standpoint. As we move around the board, we do have a status LED light, and this may be used to assist the technician in troubleshooting the heat pump. And just please refer to your factory technical information as far as flash codes and what that status light means and stuff like that. So, but we do give you a status LED for troubleshooting. Right above that, we've got the status light. Again, you can watch that status light to see what you're doing. But the thing with the test pins, now this is really important. The test pins right above that status light, if you take and you jumper those test pins. Now remember, team, you can use anything to jumper those test pins. It's a low voltage, DC voltage test pins. It's not going to shock you. It's not going to hurt you. So take anything. You could take a screwdriver, you could take a quarter, you could take a penny, you could take a key. It doesn't matter. It should be noted, though, that when you jumper those test pins, you're going to ignore the sensors. So if you're going to use a physical wire jumper, don't forget to take that wire jumper off before you walk away, because if you don't, what's going to happen, the thing will go into defrost, and it's going to stay there until you remove that jumper. And so whenever you jumper those test pins, it ignores the sensors. And remember, team, we're going to terminate defrost by looking at the coil temperature sensor. So if we go into defrost, if we force a defrost of these pins and I hold that jumper on there, it's going to just keep on defrosting until I remove that jumper and it starts to look at that coil temperature again for normal termination. So let's talk about those test jumpers a little bit more. So if I hold those test jumpers for 2 seconds and I have a Y call, in other words, if I've got a Y call from the thermostat for compressor operation. So if I have a Y call and I hold those pins, that jumper, for 2 seconds, it's going to bypass the anti-short cycle timer for servicing. Now, please note, if you jumper those test pins for less than 2 seconds, nothing happens. If I have a Y call from the thermostat, or I have a Y call are present, and I jumper those test pins for more than 2 seconds, I bypass the anti-short cycle timer. If I continue to hold that short on those test pins for 6 to 9 seconds, it'll go into a defrost. And it'll stay into a defrost until I remove those jumper pins. Now, if I force a defrost, let's say I hold those pins for 10 seconds and it's in a defrost and I remove the jumper, what's going to happen now, it's in defrost, and it will then terminate defrost as long as the coil temperature reaches the 55-degree termination point. So from a troubleshooting standpoint, watch this. If I jumper those pins, say for 10 seconds, and I go into a defrost, and let's say the outdoor coil is just packed full of ice, and I remove my jumper and it instantly jumps out of defrost, even though the outdoor coil is packed full of ice, when I force a defrost and I remove those jumper right away, if it jumps right out of defrost, I got a bad coil sensor. Because remember, once you remove the jumper from those pins, it starts looking at the coil sensor for our 55-degree termination temperature on the coil. And so that's an important little troubleshooting tip. So just remember, if you get on a job and you force a defrost and it jumps right out of defrost, but you still want to clear the coil, you're going to have to hold that jumper on there until the coil's clean. So that's kind of a nice little thing you can do. You can actually manually defrost the coil, and you can sit here and watch it and make sure all the ice gets off. If you jumper those pins and you hold the jumper on there, it ignores the sensors as long as those pins are jumpered. Now remember, defrost termination is going to take place when the coil temperature is above set point, or if you remove the Y input, it'll also terminate the defrost. And finally, once you go into a defrost, let's say, for instance, you force a defrost, if you have a coil sensor that's out of calibration, it may go into defrost and stay in there until it hits the 14-minute time backup. So either way, if you're hitting the 14-minute time backup, you got a bad coil sensor. If it jumps out of defrost right away, when you jumper it, you might have a bad coil sensor as well. And remember, team, these coil sensors will fail one of two ways. They'll fail either open, they'll just, if you put your own meter on there, it says, oh, well, they're just open. It's an open circuit. Or they'll fail shorted. They'll short together internally. And so you look at it on your ohm meter and it says, 100 ohms or something like that. And it's essentially shorted. As a matter of fact, write this down. Anything less than 1,000 ohms is considered a shorted sensor. And anything that says OL is considered an open sensor. Any questions or comments on those test pins and how I can use them to get into to force a defrost, and some of the information is telling me when I do force that defrost? Any questions or comments? Everybody good? Okay. Well, team, another couple things I'd like to talk about. Now, we had mentioned earlier that the open circuit voltage, in other words, if I remove the sensors from the board, I should be able to read 4 to 5 volt DC on those sensor pins without the sensors plugged on. Now, once I see that I've got 4 to 5 volt DC and I plug the sensor back on, that sensor is going to start sensing the temperature that it's subject to, whether it's the coil sensor or the ambient sensor. So let's talk a little bit about those sensors. Those sensors actually have a calibration point, and it doesn't matter what sensor you're looking at. On our heat pumps, they're going to be, even though they're packaged a little bit different. For instance, as you take a look at the photo, you're going to notice that there's a white sensor on the right-hand side of the photo. That's actually the ambient sensor. That's the one that just hangs out in the breeze, right? Takes outdoor air temperature. Those other sensors are going to be clamped on that you'll notice. There's some other different sensors there. They might be a tube type of sensor. They might be one that just clamps on, with a little copper clamp. It doesn't matter. They all have the same calibration point, and that's 10,000 ohms at 77 degrees. So if I take any of these sensors, and I recommend you don't soak a sensor in water, but if I take any of these sensors and I take a piece of saran wrap and I put it on that sensor and I stick it down into a cup of water that I know is 77 degrees. In other words, if I take my pocket thermometer and I go over and get some tap water, hot water, cold water out of the tap, and I know that cup of water is 77 degrees, and I take a piece of saran wrap and I put it on that sensor so it doesn't get water inside of it, although it probably wouldn't hurt it. I like to put it in saran wrap, and then stick that sensor into water that I know is 77 degrees, and I take my ohm meter, and I set my ohm meter up, and I read the ohms on that sensor. It should read 10,000 ohms or very, very close to it at 77 degrees. And that's the nominal calibration point for all of our sensors on there. Now, it should be noted these sensors are negative coefficient, which means that the resistance goes up as temperature goes down, which is exactly opposite of what we call a positive coefficient resistor or thermistor. Whereas the temperature goes up, the resistance goes up. This is exactly opposite. The warmer it gets, the lower the resistance. So resistance goes up as temperature goes down. And so, so that's, again, a negative coefficient thermistor, but they all have that same calibration point at 10,000 ohms at 77 degrees. And those can be tested very, very easily with a cup of water that you know is 77 degrees. Put some saran wrap on there so you don't, soak that sensor and the wires in water, and stick that sensor in there. You got to read 10,000 ohms. Any questions or comments on the sensors and where they plug into the board, or any questions about that before we move on? Is everybody good?
Over here.
Okay. Well, team, I'll tell you what, we're kind of, that concludes our overview this morning of our demand defrost control. So let's go ahead and open the floor up if there's any final questions or comments, and then we'll secure for the morning.
Wondering if those status LEDs on the heat pumps have a previous fault code similar to the furnaces do, because it's definitely a really handy tool.
It is. Thank you for that great comment. Yeah, to be able to look at the status LEDs on our products is pretty cool, because you can kind of look at some fault codes and current fault codes. And actually on the furnace product, you can retrieve the last 5 fault codes. If you look at it, you poke the error button, and you can retrieve the last 5 errors. And then what's really good best practice, in my opinion, is before you leave that job site, go ahead and hold that last error button down on those furnaces for 5 to 10 seconds, and it'll reset that memory for the next go round. So that's good practice there. But good comment. Any other good questions or comments before we secure this morning?
Yeah, what you just said actually brought something to my mind here. Are there any intentions going forward of including that error retrieval button on these defrost demand controls?
That's a good question. We get that asked on not a real regular occasion, but we've been asked that before. I think that's a good idea. I haven't heard or had any engineering updates or anything that said that that's anything in the future, but I can certainly make a note of that. And we're going to be doing we're still in the middle of our technical conference this week, as a matter of fact. And so I could make a note of that and ask about that. Okay, good.
Well, I'm thinking that about wraps it up for us.
Well, fantastic. Well, team, I'll tell you what, thank you again so much for the opportunity to train with you today, and look forward to our next session. Have a great day and be safe out there. Thank you.
Hey, Joel, just while I've got you on there, just a reminder to everybody that the next session is next Wednesday at 7 in the morning.
Yep, we got it.
Thanks.
Thanks so much. Have a great rest of your week.
Have a good day.